Hello. Uh, we we are studying the properties of quantiles, and the fourth property is the nonlinearity. So, quantile does not preserve addition of random variables. Uh, so, simply speaking, this is true for the mean, but it's not. It does not hold for quantiles. So here is a simple example. Simple example is given here. Suppose that you are playing a gamble. In a gamble, you throw a dice, and there are two different games. In game A, you if you see one or two, then you lose $1. Three or four, nothing happens. Five or six, you will get $1. And if you play game B, it will be plus or minus $2, but 0 when 1 or 2, 3 or 4 minus 2, 5 or 6, 2. So in both cases, so if you play a game, game A, then there are only three possible cases, minus 1, 0, 1. So median is automatically 0. So three outcomes are equally likely. So automatically it's straightforward, trivial that the median is 0. And if you play game B, also there are three equally likely outcomes, minus 2, 0, and plus 2. So median is again 0. Right? That's the median outcomes. Now, then let's think about the game that you are playing both. So you are betting on both A and B. And then if you see 1 or 2, your total outcome is minus 1. 3 or 4, the total outcome is minus 2. And 5 or 6, you get $3. And then there are three outcomes, minus 2 or minus 1 or 3. And again, these three outcomes are equally likely because they are determined by dice. And if the dice is fair, then exactly the probability is 1/3 for each of the outcomes. Then in these three outcomes, the median is now the middle one. So minus 1. This is the problem. So median of A was 0, median of B was 0. The median was A plus B becomes minus 1, which even in this simple example, you may construct a very interesting counterexample, and so it causes many problems. For example, we used this equation a lot. Excuse me. We use these equations a lot, but it is not true anymore. Quantile regression does not have this kind of expansion, so it does not work. So this tab is broken, so it restricts the quantile regression in many dimensions. So instead, the quantile dimension have a quantile operator has a similar equation like this. Quantile goes like this, and so conditional on x. This part, because x is conditioned, this part is non-random. Because when x is given, then it is not random anymore. And then beta is non-random, so this is a constant. It is not a random number, conditional on x. So you can just put it outside of the quantile because it is constant. So you are applying the monotone transformation rule, not addition of random variables. So it is about addition of random variables, but in this case it is not addition of random variables anymore because it is constant. And finally, when the mean regression and the quantile regression are the same, consider the mean regression goes like this, and the median regression is written this way. And by the way, the coefficients alpha, the intercept alpha, and the slope beta may be different if you use a different quantile. So different quantiles imply different coefficients. So here, like we are going to consider median, but I will keep keep tau. The dependence of the coefficient on tau is explicitly denoted. And the first case, if the distribution of epsilon conditional on x is symmetric, then mean regression is equivalent to the median regression. It's intuitive. And think about this. Say the quantile of epsilon does not change as x changes. Conditional quantile is the same for all values of x. And then simply suppose that we are going to let this value to be a. Then remember, this is also different from this. If the error terms are different, but we are handling the error term from the mean regression, and the mean regression has this quantile, then we may use the same logic. So as long as if the quantile of epsilon, the distribution of this error term does not change as x changes, then you may transform this regression into a median regression or a quantile regression by readjusting the 0 point. 0 point is adjusted by a, and then you may construct the quantile regression error term this way, and just intercept may be different, but the slope is the same. And finally, another case is when the quantile is linear in x. So in this case, quantile may change as x changes, but the pattern is linear. Then this linearity can be observed into the slope. So the mean is the same, but the quantile may be different, may go up or go down. So, but if that trend is linear, then if you reflect the trend in beta, then you have a median regression derived from the mean regression. So this is the simple relationship between and finally, if epsilon is statistically independent of x, it is a complete independence. Then same thing happens. Like it's equivalent to case 2. So you have the same slope. Slope does not change, but you have to readjust the 0 point. So that is the relationship between the mean and the quantile regression. Okay, I'm going to continue in the next video. In the next video, we will talk about the serious identification and estimation problems. See you later.